Welcome to this first video in our complete course on modern physics. In this course, you will build a strong foundation and gain an in-depth, comprehensive understanding of modern physics. Whether you are new to the subject or looking to deepen your knowledge, this course will provide you a holistic approach to mastering modern physics concepts. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the very first video in learning modern physics. Well, what actually is modern physics? Before going into that, I would like to show you this extraordinary photograph. Now, this extraordinary photograph immortalizes the minds who actually pioneered modern physics. They were present at the 5th International Congress of Physics in 1927, hosted by the Solvay Institute in Brussels. Here, the creators of modern physics gathered, passionately exchanging ideas and insights that would reshape our understanding of universe. As you know, among this distinguished assembly are 15 Nobel Prize winners in physics and 3 in chemistry, united as the architects who laid the foundations of modern scientific thought. If you are living, or if you are a physicist who is living in the 19th century, you probably would have been pleased with the progress that physics had made in understanding the laws of nature that govern the process of nature. Newton's laws of mechanics, including gravitation, had been carefully tested, and their success had provided a framework for understanding interactions among objects. Electricity and magnetism have been unified by Maxwell's theoretical work, and electromagnetic waves predicted by Maxwell's equations has been discovered and investigated in the experiments conducted later by Heinrich Hertz. The laws of thermodynamics and kinetic theory had been particularly successful in providing a unified explanation of a wide variety of phenomena involving heat and temperature. So what you see on the screen, 3 successful theories, mechanics, electromagnetism and thermodynamics, form the basis of what we called classical physics. Taking our horizon beyond your 19th century physics laboratory, the world was undergoing rapid changes. The Industrial Revolution demanded laborers for the factories and accelerated their transition from a rural and agrarian to an urban society. These workers formed the core of an emerging middle class and a new economic order. Now, the political world was changing. The rising tide of militarism, the forces of nationalism and revolution were actually going to soon upset established governments. The fine arts, similarly, was in the middle of a revolutionary change, as new ideas began to dominate the fields of painting, sculpture and music. The understanding of even the very fundamental aspects of human behavior was subject to serious and critical modification by the Freudian psychologists. Now, in the world of physics, there were undercurrents, and that would soon cause a revolutionary change. Even the overwhelming majority of experimental evidence agreed with classical physics. Several experiments gave results that were not explainable in terms of otherwise successful theories. So there was a question mark. Now, classical electromagnetism theory suggested that a medium is needed to propagate electromagnetic waves. But precise experiments failed to detect this medium. Experiments to study the emission of electromagnetic waves by hot glowing objects gave results that could not be explained by classical theories of thermodynamics. Similarly, experiments of the emission of electrons from the surfaces illuminated with light could not be understood using classical theories. All this actually contributed in setting the stage of what is called modern physics. Now, if I go by the definition of what is modern physics, we can tell that the physics that was developed during the early 20th century, or you can say the branches that influenced the early 20th century physics, is actually what is called modern physics. So we can define modern physics as basically an effort which is made to understand the underlying process of the interactions of matter using the tools of science and engineering. If you are wondering about what would be the timeline for modern physics as a whole, well, the physicists and historians, some say between 1900 to 1920, but it can be actually taken a little bit far beyond 1930 also. So what are the major things which constitutes of modern physics? Let us look into that. The first, it comes with Einstein's theories of relativity, which includes both special and general. The world of the very, very, very small, that is the quantum mechanics. And the world of very, very, very small, but on a relativistic notion would be quantum field theory. There was a huge change in terms of the standard model of particle physics, and it took us beyond the night sky, that is cosmology, astrophysics, and different areas of science. So this would constitute the idea that what is modern physics, the time, the era, and what are the subjects of science that are involved. Now, one thing which becomes extremely important is that the most of the part of modern physics depends upon what is called classical physics. So we think that reviewing some of the very classical concepts of physics is essential because it provides the foundational principles. Also, you will see that understanding classical concepts basically helps us to understand the limitations and thereby how to overcome the limitations in order to create a new theory, maybe quantum mechanics and relativity. So in the next part of the video, we are going to make a very quick review on certain concepts of classical physics, and here we would start first with mechanics. Now, suppose a particle of mass m is moving with a velocity of v and has a kinetic energy which can be defined as half mv squared. And it also has a linear momentum p which can be defined as p equals to mv. And in terms of linear momentum, there is also kinetic energy which can be defined as this. So suppose one particle collides with another particle. We analyze the collision by applying two fundamental conservation laws. And these are basically the law of conservation of energy and the law of conservation of momentum. Now, if we go by the understanding and definition of the conservation of energy, then it tells that the total energy of an isolated system, that means on which no external force acts, which is very important, remains constant. So in the case of a collision, which we just noticed, between particles, the total energy of the particles before the collision is equal to the total energy of the particle after the collision. So we can write something like this, E total equals to E kinetic plus E potential, or maybe there are some other forces which leads to constant. And in a simple way, we can write E initial is equal to E final, where E denotes energy. The conservation of linear momentum, it says that the total linear momentum of an isolated system remains constant. So in case of a collision, the linear momentum of the particles before the collision is equal to the linear momentum of the particle obviously after the collision. So because in linear momentum is a vector, its application of the law can be used as P initial would be equal to P final. And if I take two bodies of M1 and M2 separately, then we can write as M1 V1 plus M2 V2 equals to M1 V dashed 1 and plus M2 V dash 2. Obviously the dashed means the new particle which will come or after the collision. Now what becomes extremely important to understand is that these two conservation laws are the most basic importance to understand and analyze a wide variety of classical physics. And you will see that as we go ahead, these laws become so important. And also what it is important that all these equations, P equals to mv, this one, and the kinetic energy, these are actually modified. They are actually greatly modified using the special theory of relativity. So we will see up in the further sequence of videos. So special relativity modifies these equations, but these two equations, the law of conservation of energy and the conservation of momentum, remains valid. So let us, understand one thing, that although special relativity, as we will see, will change and modified, however, these two equations are basically same, that they won't modify, and in terms we can say invariant. Now this mechanics of the classical physics that we are looking, we will take an example and let us look into that. Now I would like to take an example, say for example an atom of uranium which has got around this kind of a mi mass, which is at rest and decays spontaneously into an atom of and there is an atom of thorium, right, and there is an atom, it spontaneously decays into, so the uranium atom spontaneously decays into an helium atom and an atom of thorium which has got a mass something like this. Now the helium atom is observed to move in the positive x direction, right? It will move in the positive direction. It has got a velocity of this one, 1.423 times 10 to the power 7 m per s, and what we need to find out is this one. Find the velocity, that means magnitude and direction of the thorium atom, as well as the total kinetic energy after the decay. Now what we are going to do in this kind of an example, let us first look into this diagram. Diagram always makes things clear. So you can see the uranium atom, the thorium atom and the helium atom are already have denoted by this dashed sign V prime He. So here what we would do is that this is the uranium atom, this is the thorium and helium atom. So we will use the law of conservation of momentum. So what do we do? The initial momentum before the decay is 0. And the total momentum of these two atoms after the decay also must be 0. So what we can do is that P initial would be equal to 0 and P final would be equals to this plus this. Now if you are feeling a little bit confused about these TH and M and HE, don't worry, these are all subscripts in order to make the mathematics a little bit easier. These things will become very clear in a few minutes from now. Now what I'm going to do is I am going to turn the page and I'm going to take the same equation and I'm going to set P initial equals to P final, and solving for V prime TH, that is for thorium, we will get something like this. And if I substitute the values, which you can pause, take a note or do the calculations as yourself, I will get something like this. Now note that the thorium atom actually moves in this direction, which is a negative x direction. So we have got a negative sign. Now the total kinetic energy after the decay is this one. And if I substitute the values now, I get something like this and this. And finally we get this one amount of joules. Now one thing which becomes pretty clear from this mathematical calculation, 6.844 times 10 to the power minus 13 joules, is that clearly the values I get from here and here and here and here. Just wanted to show that these the values in the numerator and denominator, how they do. And this negative is because the thorium is moving in the negative direction. So these are the values. But remember one thing, clearly the kinetic energy is not conserved in this decay. The kinetic energy is not conserved in this decay because the initial kinetic energy of the uranium atom was 0. Let us look into the next page so that we can write these equations in a much better fashion. So this uranium atom is not conserved in this decay. Why? Because the initial kinetic energy of the uranium atom was 0. However, what becomes important is that total energy is conserved. That means if we write the total energy as the sum of kinetic energy and nuclear energy, then the total initial energy, that means kinetic plus nuclear, is equal to the total final energy, which is again kinetic plus nuclear. So the gain in kinetic energy which you just saw occurs as a result of a loss of nuclear energy, and this is typically what is called a radioactive decay, or we can call it an alpha decay, which we will discuss in the due course of time in this series of learning modern physics. So this is one example of using this atom and showing that how mechanics energy, total kinetic energy is conserved and how it happens. Now let me take you through another very interesting example. Let us take a particle which I have made a little bit bigger. Say for example this is a particle, okay, and the principle of conservation of energy occurs when a particle moves in this direction, which you can see in this direction, subject to an external force which is F. So the principle of conservation of energy occurs when a particle moves subject to an external force F. Now, corresponding to that external force, there is often a potential energy, which is this one, denoted by U, such that, I mean to say, for one-dimensional motion, we get some kind of an equation like this. And the total energy, E, that means this one, E, is the sum of the kinetic and potential energies. But as the particle moves, this this K and U might change. As the particle moves, K and U, that is the kinetic and the potential energy, may change, but this one, E, will remain constant. And remember that when we will learn special theory of relativity, it will give you a totally new definition of what is called total energy. So now I hope you can understand that why I am giving a review of the mechanics, so that you can understand that how these things are going to take a complete turn, complete transformation when relativity will come into account. Let us take another example, which is, I would say, a very important concept. Say, for example, when a particle is moving with a linear momentum, say, for example, this, with a displacement r from the origin O, then its angular momentum L equals to r times p. Let me show you a quick diagram. So this one, if you look into this diagram, you see that the particle of mass m located with respect to the origin O by position vector r and moving with a linear momentum p has an angular momentum L about O. Now, there is a conservation for angular momentum just with linear momentum in practice. Now, for example, when a charged particle, for example, this one, a positively charged or any charged particle, this charged particle moves near, and if this particle comes near and is deflected by another charged particle, so this is the deflection, the blue one which is going, the total angular momentum of the system, that is of the two particles, remains constant. I mean to say, obviously, if there is no external torque which is acting on the system. Now, if I take a second particle which is much more massive than the first, that its motion is essentially unchanged by the influence of the first particle, the angular momentum of the first particle remains constant. Why? Because the second particle acquires no angular momentum. Another application you can use is the conservation of angular momentum when a body such as a comet, which moves in the gravitational field of the sun, the elliptical shape of the comet's orbit is necessary to conserve angular momentum. So the elliptical shape of the comet or the body, celestial body, is necessary to conserve angular momentum. What will happen? In this case, both r and p of the comet must simultaneously change in order to make this L remains constant. So I would say this is another understanding with another example. Now, in terms of mechanics, what becomes a very important aspect of classical physics is called combining velocities or adding the velocities together. For example, suppose a plane is moving at the velocity of vpg. Now, this pg again is basically velocity of the plane relative to the ground. So the subscripts are basically velocity of the plane relative to the ground, vpg, plane relative to the ground. And the plane fires the missile in the forward direction. I have just made it a little bit tilted, but anyway, you can think of a forward direction. And the velocity of the missile relative to the plane is this one, 250 m per second. Now, according to the observer, for example, this observer who is staying on the ground, the velocity of the missile is this one plus this one, which is equals to 900 m per s. Now, this is something specific, but we can generalize this rule. Now, say, for example, if I take 3 points A, B, and C, so VAB, for example, this one represents the velocity of A relative to B, and let VBC represents the velocity of B relative to C, and for example, the velocity of A relative to C would be equals to this. This is a kind of a generalization. Now this equation is written in vector form to allow for the possibility that the velocities might be different in different direction, because the missile might be fired and in the direction of the plane's velocity but in some other direction. Now this seems to be a very common sense of way of combining velocities, but we will see in this series of videos that in the common sense rule led to contradiction when things appear to move close to the speed of light. That means in terms of special theory of relativity, it won't be that same. I won't say easy. Definitely it is something easy to compute, but it won't be same. So this would again change. So that is why review of the vector addition is required. Now let us analyze this one, the vector addition, in terms of, say for example, in this term. So in a frame of reference that is moving with the center of mass, suppose the initial velocity of this helium atom is this one, and in the positive x direction. So the velocity of the center of the mass relative to the laboratory is then this one, VCL equals to this plus this divided by this plus this, which can be taken in terms of numerical equals to this. And what we are trying to find out, this one is the velocity of the center of the mass. So what we are trying to find out is that the initial velocity of the helium and the n. Right? So what we are going to do is that we would like to find the initial velocity of He and E. So we would first start with this one. And from here what we get, first you have a look onto the subscripts which I have used, because this might be a little bit confusing, but I have used deliberately in order to make you understand. So L is laboratory, C is center of mass. So this makes things specific. So we go to the next page and we take the same equation, and here what we do is that we are substituting the values, which takes a little bit longer, 1.181 10 to the power 6 m per s, and VNC would be something around negative 0.337 etc. And in similar way you can calculate the final velocities of He and n, and the resulting collision would be something looking like this. So each velocity simply changes direction, leaving its magnitude unchanged, and the atoms move in opposite direction. Because the velocity addition in this case applies only to the x components and leaves the y components unchanged, which means that the angles must change. So this is another example of vector addition in terms of collision of particles. Now it is the time that we move from classical mechanics, I'm going to say from the vector addition classic mechanics about electricity, because this is also important. We'll see how things again change in terms of special theory of relativity. Now the electrostatic force or the Coulomb force exerted by a particle such as Q1 on another charge Q2 has a magnitude of this. And the direction F, as you can see right on this picture, is along the line joining the particles. Now in the SI systems of units, the constant 1/4 pi epsilon naught has the value of this one. This is the value, and there is a corresponding potential energy, which is this one. Now you can see in all the equations that we have seen here, one thing is very common. That is 1/4 pi epsilon naught, it always appear. But here is a note of caution. In some texts and reference books that you might read in modern physics, you may find electrostatic quantities in which the constant does not appear. It is not there. If it is not there, understand that in such cases the centimeter gram second or the CGS system has been used, and which this constant 1/4 pi epsilon naught is reduced or defined as 1. And you should always be careful in making comparison of electrostatic quantities from different references and check that the units are actually identical. Otherwise you might face a problem. Now an electrostatic potential difference, which we called as delta V, can be established by distributing two charges. The most common example, for example, here I have used a battery which has got the two terminals. Now when a charge, say for example this Q, moves through a potential difference of delta V, then the change in its electric potential energy of delta U would be this one, delta U equals to Q times delta V. Now remember that this might create a problem. What is that problem? The problem is that in the atomic or nuclear level, when we measure, we usually measure charges in terms of the basic charge of the electron or proton. So when we say a basic charge, what is that? Its magnitude is E equals to this one in coulombs. Now, if such charges are accelerated through a potential difference of delta V, that is, say for example, few volts, if I'm going to accelerate this, then the resulting loss in potential energy and corresponding gain in kinetic energy will be of the order 10 to the power minus 19 to round about 10 to the power minus 18 joules. Now, in order to avoid working with very small these kind of numbers, it is common that in the realm of atomic or nuclear physics to measure energies in terms of eV or electron volts. And this is defined to be the energy of a charge equal in magnitude to that of the electron passing through a potential difference of 1 volt, which is going to be this. I've shown the calculation, but I mean to say you can just ignore. This gives us a better calculation, not in terms of big numbers, but in terms of this. And so from here we can get some very beautiful things. We can get 1 electron volt equal to this, and the table looks like this: kilo electron volt, mega electron volt, giga electron volt. Now there are certain references you might find BeV, that is billion electron volts, but these are actually old references. So if you wish to find, the question is now this, that how can we calculate the potential energy between two charges which are separated by atomic or nuclear distances in electron volts? How do we do that? First, we express this quantity E square by 4 pi E epsilon naught. I'm sorry, this epsilon, this naught would be at the subscript, but anyway, you can take this value, and substituting we get this one, and further we get this one. Now, this useful combination, one thing is very important to note here, that you see that this, if there are two electrons, for example, and they're separated by by a typical atomic distance of 1.00 nm, 1.00 nanometer, then what we can see is this one. This equation will now go into this one, 1 by r obviously, and substituting the values we get 1.44 eV. Remember, just now I have showed that how those joules etc. can be changed to electron volts, because we are working at the nuclear atomic level. So for calculations at the nuclear level now, we measured them in terms of femtometer. It is a more convenient unit of distance, and MEV, that is mega electron volt, more appropriate for energy unit. So E square by 4 pi epsilon naught will reduce to this, which will be equal to this. Now here, this is something very important to note, that this E square by 4 E epsilon naught number has not changed. So here as well as in here and otherwise, this has been constant. And it is very easy to memorize also, 1.440. So the thing is that this E square by 4 pi epsilon naught has the same value 1.440, whether we use atomic energy sizes, that is eV nm, and typical energy sizes, that is mega electron volt or FM. So that makes the memorization easy, and that makes the mathematical calculations easy. So we take a pause for today's video, where we have understood what is modern physics. We have reviewed some of the concepts of classical mechanics and electricity. We have to review a few concepts more on magnetism and kinetic theory of matter, and then we will go forward into the real modern physics. And this will be continued in my series of lectures on modern physics coming up very soon on this channel. So as you can see that this is a green tick, so it is always the same. So thank you very much for taking your time and I would say watching this video. If you've liked this video, do not forget to subscribe and hit on the bell icon to get all the notification from Physics for Students. You can write to my email ID and you can subscribe and like my other channel, General Relativity Explained. You can also follow me on my Facebook, Instagram, LinkedIn and Twitter account. Physics for Students will be soon back, continuing with this series on modern physics. But till then, may the good Lord be with you.